Components. The performance of articulated robots depends significantly on its main components. These components are grouped into links, joints, and end effectors. An end effector is a device which is specifically designed for the attachment to the mechanical interface to enable the robot to perform its task. These are usually welding guns, grippers, painting nozzles, or less commonly, motor spindles. There are other components, such as kinematic parallelograms, which potentially improve robot stiffness and decrease energy consumption, as well as gravity compensators, which do not affect essentially the manipulator stiffness, but reduce the torque in the actuated joints induced by the external loading, which allows for either greater wall thickness or lower energy consumption. Kinematic parallelograms seem to be less frequently featured in later industrial manipulator designs as they increase the footprint. End effectors are diverse and may feature several actuators and sensors themselves. For example, the DLR hand that you see in the main figure features rotary encoders and strain gauges for the force measurement to ensure that the egg is securely fixed but neither squished nor lost. Links are interesting from a geometry optimization point of view, that is, their weight, stiffness, manufacturability. Nevertheless, those will not be discussed in this lecture. We will solely focus on the components that are used in robot joints. Joints. As aforementioned, joints, usually revolute joints, enable relative movement between adjacent links. For that purpose, they feature motors, transmission systems, a measuring system, and potentially additional sensors. Almost all industrial manipulators feature mechanical drivetrains. These consist of AC or DC motors to convert the electrical power into mechanical power to provide the torques for the movement of the links, and a transmission system. The transmission system is required as a direct drive is usually not suitable for industrial manipulators, as they commonly require high torques. The mechanical transmission system converts a high number of rotations and a low torque into a lower rotational velocity and a high torque. The most commonly used transmission systems are harmonic gears, rotary vector drives, and planetary gears. All of these gears try to minimize backlash. The disadvantages of harmonic drives are elastic wind-up, that is, the torsional stiffness leads to a distortion which has a similar effect as backlash, and their lower stiffness, while the other gears usually feature a low stiffness at zero torque due to their play. The measuring system provides feedback about the motor or joint position to the robot controller on the driving side. This information is used to calculate the positions of the end effector as well as all links in space to ensure that no spatial velocity or acceleration constraints are violated. Robots that are meant for tasks that require higher accuracy, less than, let's say, 0.25 mm under load, may additionally feature some or all of the following sensors. A sensor to measure actual current, that is the difference from the nominal current used for the control of the robot, to calculate the acting torques in the joints. A position sensor double encoding, which measures the rotation on the driven and the driving side of the gear, and a force torque sensor, which can be used to identify the load at the end effector. According to the International Federation of Robotics, only about 10% of the installed robots have any of these additional sensing capabilities. As aforementioned, most industrial manipulators feature mechanical drivetrains. Nevertheless, you will also find manipulators that have hydraulic or pneumatic drivetrains. Such as the Festo Bionic Cobot. It is a pneumatic system where the pressure in the joints leads to It is a pneumatic system where the pressure in the joints can be used to set the stiffness of the end effector. Then, another thing when it comes to robot design, which I think is interesting and one may consider, that there are also manipulators with a hyper-redundant design, or also called a continuum manipulator, which means that the number of joints tends to infinity while the link length tends to 0. So there are two examples which I would like to show you here. There's one which is more oftenly commercially used, this kind of snake arm which is used for laser welding. And then there are other ones, such as the Festo Bionic Handling Assistant, things sometimes also referred to as the bionic trunk, which could be, for example, implemented on a dual-arm robot as a single arm.